Okay, I take this chance to welcome you to Ambassador Foundation learning that is always taking place at that channel. And I would like to thank you on behalf of this foundation for watching, subscribing, and learning from here. You are allowed to comment, you are allowed to share, you are allowed to make any advice to us. Our team will be back to you. So, any day you see a new day, it's another chance to better your best. It's another chance to do what you are unable to do the previous day. So this day I welcome you to a physics lesson, and we are still looking at what we call the quantity of heat. The other day, the previous lesson, you saw it. If you have not seen it, you can go back and check on it. We looked at the quantity of heat introduction, we looked at the heat capacity, we looked at the specific heat capacity, we looked at their units and how they are being calculated. Now this day, I want us to look at a very simple concept, which I know from where you are, you can get this concept. I want us to discuss on how we can find the specific heat capacity of a substance. Substance can be a solid, a liquid, or even a gas. So, we are going to use various ways. The first method that we can use to find the specific heat capacity of a substance is what we call the method of mixtures, which we are going to check it right now. The other one is what we call the electrical method. We all know that a current can cause a heating effect. So, a heat produced by a current can raise the temperature of a substance, can change a state of a substance. So, it's also possible we can find the specific heat capacity of a substance using electrical methods. Then another one, which may be at your level, we are not going to discuss it, but I can just state it for you, is what we call the continuous flow method. It's that method which, if you get interested in physics, high school, you will still do it in university, you will meet with continuous flow method. So for now, let's look at the method of mixtures. Very interesting. Enjoy the lesson. So now, at some point, you've ever wished to take a warm bath. You have cold water, you have hot water. You put them together, the hot water will drop in temperature, the cold water will rise in temperature. So now we are mixing the cold and hot. That's why we are calling it a method of mixtures. So by the time you mix them, at a given point, the two of them will agree at a common temperature. Maybe you mix a given mass of water at 100 degrees Celsius, another one at a room temperature maybe at 25 degrees Celsius. Then when you mix them, they will settle at a given temperature, let's say 50 degrees Celsius, depending on which mass, either the cold or hot, was large. That's what we are going to see. At some point, you've made a mistake. You wanted to take a very warm bath. Then you mix a large amount of cold water with a small amount of hot water. Then you end up taking a cold shower, by the way. But after learning this topic, after learning the concept of today, you will never make such a mistake again. If you want to take a warm bath, you will, because you will know how to mix what amount of cold water, what amount of hot water to put them together. For you to understand this concept of method of mixtures, I want you to do yourself a favor. You can also do me one favor. Just notice that the heat gained is always equal to the heat loss. The heat gained is always equal to the heat loss. And there is one assumption we are making here. We make an assumption that there is no any other heat gained from the outside, and there is no heat lost to the outside. So we make an assumption that whatever the substance that is losing heat, all of that heat lost by that given substance is gained by the one that is gaining the heat. So the assumption here is no heat lost to the surrounding. The common one is whereby we use a calorimeter. A calorimeter is a locked container that you can place a certain liquid inside. Then we put another material with a very high temperature so that it's going to lose heat to the calorimeter, and to the liquid inside the calorimeter. It is locked. It is locked, meaning it has been made in such a way that it cannot lose heat to the surrounding. Neither can it gain heat from the surrounding. So we are going to check. In fact, if you want to understand this, there are two questions that I've just written on the board for you to understand and enhance your concept on this. Heat gain, don't forget this. The way you remember your name, two names, heat gain is the same as heat loss. And you're going to check on this. So you remember what we did last time? We said what? We said that the quantity of heat is given by M, specific heat capacity, times change in temperature. That is what we are going to follow all through. Whatever the question that you are given, just the first task, identify the substances or substance that is losing heat, then identify the one gaining heat. You will be able to get it. So, you may have two substances, like the cold and hot water I was telling you. You are given their masses, the specific heat capacity, and their change in temperature. The one that is not given in that question, just be very sure it is the one that you will be required to calculate. We will give you complete in other substances, their mass, their specific heat capacity, the change in temperature. Then in other cases, we give you but we deny you either the mass, either the specific heat capacity, then we'll ask you to find it for us. That's what now the method of mixtures. But the common thing is identify the one gaining heat and then identify the one losing heat. There is one concept I would like also you to notice. You will be told this as we are going to check on these questions. You will be told this, that a given liquid in calorimeter is at a given temperature, let's say 15 degrees Celsius, but no one will tell you the temperature, the initial temperature of the calorimeter. No one will tell you. But if the water in the calorimeter are at 20 degrees Celsius, are at 25 degrees Celsius, then that is also the temperature of the calorimeter. That is the initial point. Then we are going to drop it, either a metal or any substance from a very high temperatures, like 500 degrees Celsius, that's from an oven. You drop it in the liquid. So the one with the high temperatures will cool down. The one with very low temperatures will rise up. So they somehow accommodate each other. That's why if you want to choose a friend and you are always a short-tempered person, look for a friend that is not short-tempered, so that you can balance each other. One can cool the other. So let's read this question as we are marking the key points, as we are marking the what are we supposed to know, then we answer it without hurry. We say that there is no hurry in Africa, and we are the one owning Africa, but leave that alone. A locked copper calorimeter of mass 0.75. That's the first thing to note. This calorimeter has a mass of 0.75 kilogram. It contains 0.9 kilogram of water. It contains 0.9 kilogram of water at 20 degrees Celsius. That's now where we need to talk for a second. At 20 degrees Celsius. If you read this very well, it is as if it is the water that is only at 20 degrees Celsius. But trust me, both the calorimeter and the water are at 20 degrees Celsius. Good. So, and for your information, there is a high chance these two are the one that is going to gain heat from a ball of mass 0.8 kilogram is transferred from an oven. Oven is a fiery furnace, whereby if you don't get born again, you will go to hell. Hell is an oven. From an oven at 400 degrees Celsius. Now, this ball has a mass of 0.8 kilogram, and the initial temperature of the oven. Sorry, yes, at the oven is 400 degrees Celsius, but when we remove it, that bowl will also be having the same temperature as what is taking place in the oven. To the calorimeter, and a steady temperature of 50 degrees Celsius is reached by the water after stirring. The game short. Calorimeter, water gaining heat. Cold losing heat. The whole heat lost by the pole, all of it is going to be gained by the two substances, that is the calorimeter and the water. Now, so we make an assumption that there is no heat loss here. We make an assumption there is no heat loss. So heat gain is the same as heat loss. So we need to find out what are the substances gaining heat, and we already know it. Water and the calorimeter. Then now, of course, at some point there, we are supposed to be given some specific heat capacities of the substances, but we are going to be denied of one of them so that we can calculate it. Let's finish the question. Calculate the specific heat capacity of the material of the bolt. Nice. Specific heat capacity of the copper is 400 joules per kg per Kelvin, and that of water is 4200 joules per kg per Kelvin. Nice. So let me write here. Water is gaining heat. Water is gaining heat. So the heat gained by water is mc, change in temperature, or change in theta. So the mass of water from the equation is 0.9 times 4200. That is the specific heat capacity of water, times the change in temperature. What is the change in temperature? The change in temperature is this. It was at 20 degrees Celsius, and finally it finds itself at 50. The change in temperature is 30. We are given in degrees Celsius, but I'm writing it in Kelvin, times 30 Kelvin. This one will give us a value here, which we are going to give it. Let's look at the calorimeter. Calorimeter. Some will tell you calorimeter, it doesn't matter. It's the effects of potatoes. What's the mass of calorimeter? Because also it's going to face the same way. Its mass is 0.75 kilogram. Then we multiply by the specific heat capacity of copper, which we are told is 400. We have the 400 here. So times 400. Then we multiply by the change in temperature, which is the same as that of water, because they were at the same temperature and they will settle at the same temperature. Then we will get that heat. These two are gaining heat. From where? From the bolt. Let's do it. Let's take a hit. I always say that, now make use of the calculator your parent bought for you. I know you don't have money to buy a calculator, but you need to thank your parents for doing that for you. This one gives me 113,400. 113,400 joules. If I'm not wrong, confirm from your site. This one also is giving me now 0.75. There are some of you, they don't know how to use a calculator, but when you give them a smartphone, they can utilize it fully. That is when you will know the devil is joking with your destiny. 9,000 joules. The 2 is the heat. So heat gained. It's going to be 113,400 times 900. 9,000. We get, let me add, plus 113,400. 122,400 joules. Now, these 122,400 joules are the one that's going to be lost by the volt. So in very short while, I can just say 122 400 joules should be equal to the MC change in temperature of the bolt. What's the mass of the bolt? Are we given? A bolt of mass 0.8 kilogram times, we are told now we calculate the specific heat capacity the bolt is made of. So times C times change in temperature. What is the change in temperature? From 400 degrees Celsius to 50 degrees Celsius, it dropped in temperature by 350 Kelvin. That is it. So 122 400 should be equal to 350 times 0.8, 280 C. So our C is going to be 122 400 divided by 280. 122 400 divided by 280. So I get this 437.143 joules per kg per Kelvin. Now tell me what is so hard with that question. You've just done it very well. You have now the answer. It's a good question. Try to understand this. It is also a very strong paper 1 question that if there's any candidate learning from here, there's a high chance this question is always there. It has never missed. So your ear is not special that it will miss. Another question. A block of mass. Let me clear the board first. You can be reading the question in the meantime. But let's read together. A block of mass 1.25 kilogram. I say that anytime we are doing this, we mark the keywords. A block of mass 1.25 kilogram at 120 degrees Celsius was transferred to an aluminium calorimeter of mass 0.3. So today we are using aluminium. The calorimeters are made of different materials. In this case, the former case was copper, now it's aluminium. It has a mass of 0.3 kilogram containing a liquid. So it's not water, it's a liquid of mass 0.6 kg at 25 degrees Celsius. So the calorimeter, the liquid, and their masses, all of them are at 25 degrees Celsius. Now the block and the calorimeter with its contents eventually reached a common temperature of 50 degrees Celsius. So calorimeter and the liquid, they gain heat from 25 degrees Celsius to 50 degrees Celsius. So the temperature is 25 Kelvin. Given the specific heat capacity of iron as 450 joules per kg per Kelvin, and that of aluminium 900 joules per kg per Kelvin, calculate the specific heat capacity of the liquid. This one should be for aluminium. That must be where the error is. The question is talking of the specific heat capacity of iron. Then it has given us aluminium. I wrote that specifically so that you know how to use your head sometimes. Where is iron? It's for aluminium. So, okay, well, now, the ones gaining heat, we are supposed to find the heat gained. Then, we are supposed to find the heat lost. So, I will combine this one. I'm not going to break it like we did in our first question. I will just do it once. The heat gained is equal to the heat lost. So now, those gaining heat, mass of the aluminium times specific capacity of the aluminium times the change in temperature plus the mass of the liquid, specific heat capacity of the liquid, times the change in temperature should be equal to the mass of the block of mass, the mass which is now, I will just write B for the block, times at the specific heat capacity of the block times the change in temperature. Yes. So we are being asked to calculate the specific heat capacity of the liquid. Calculate the specific heat capacity of the liquid. Now, aluminium, what's the mass of aluminium? The mass of the aluminium, this is the calorimeter now. So we just go back to the question. A block of mass, 1.52 kilogram at 120 degrees Celsius was transferred to an aluminium calorimeter of mass 0.3. So it's going to be 0.3. Do we have the specific heat capacity of aluminium? Yes, 900. What is the change in temperature of aluminium? From 25 to 50. From 25 to 50. So it is times 25. Then plus mass of the liquid. Are we given the mass of the liquid? 0.6. 0.6 times C, because we are not given the specific heat capacity of the liquid. It is the one we are looking for. Times what? The change in temperature, which is times 25. Should be equal to the mass of the block, 1.25. Now times the specific heat capacity of that block. This block is the one that is being referred as iron, which is now, we are told to be 450. What is the change of temperature? What is the change of temperature of this iron block? From where? From 120 all the way up to 50. There are those who will take their calculators, 120 minus 50. There are those who will write down, and then we have you that you just know very well. 120 minus 50 is 70. Let's now do it. Up to where we are now, in fact, you are not the one to do it. It's your calculator to do it. Just key in those values. Your calculator will do it. 0.3 times 900 times 25. I know some of you will still be unable to use a calculator. If your parents have bought for you the calculator, again you want them to teach you how to use a calculator. No one taught you how to use a phone. Times 15. This one will give us 15C. Should be equal to 1.25 times 450 times 70. During our times we didn't use calculators, but let me just use now because it is available. Times 70. 1.25 times 450 times 70. It's giving me 39,375. 39,375. That's 9,375. So we collected the like terms. So 15C should be equal to 39,375 minus, it's a positive. When it crosses the equal sign, it becomes a negative. So 39,375 minus 6750. 6750. We get 32,625. 32,625. Then the value of C. So you take that answer and you divide by 15. You get 2175. 2175. Because it is a specific heat capacity, the units are going to be joules per kg per Kelvin. Joules per kg per Kelvin. Once again, have you seen anything difficult there? These questions are so simple. The concepts are very simple. Please don't make it difficult. You have the ability to make a question difficult, to make a concept difficult, or to make a given topic difficult. the last question. I read it for you so that we can do it together. Write it down. A man wants to take a warm bath. Really? No. This one should be a woman. We men don't take a warm bath. Okay, anyway, a man wants to take a warm bath at 40 degrees Celsius. Find the mass of water at 100 degrees Celsius. Find the mass of water at 100 degrees Celsius. He will add to 4 kilograms of water at 20 degrees Celsius. A real man should put water in a fridge so that he can take bath. When you see any man warming water to take a shower, when you see any man warming water to take a shower, say hi. She is Sharon. She deserves to be called Sharon. Now, we have warm water. Warm water here. Or, no, this one should be hot. Hot water. 100 degrees Celsius. And the mass, we don't know. Then we have cold water. Even this one, we don't have the specific heat capacity, no problem. Cold water, it is at 20 degrees Celsius and its mass is 4 kg. Now, you are being asked a very simple question. What is the mass of the hot water that should be added to the cold water to bring it to a common temperature of 40 degrees Celsius? So the heat gained by the cold water should be the same as the heat lost by the hot water. So I'll write here M of the hot water, specific heat capacity of the hot water times the change in temperature should be equal to the mass of the cold water, specific heat capacity of the cold water times the change in temperature. Now that the two liquids, all of them are water, they have common specific heat capacity. I just remove it. So the mass of the hot water, we don't know. But the change in temperature is from 100 to 40. So that is times 60. Should be equal to the mass of cold water, which is 4, times the change in temperature from 20 to 40 times 40. I mean, from 20 to 40, it's no longer 40, it's times 20. So we can get this mass of hot water. The mass of hot water is going to be simply 4 times 20 is 80. 80 divided by 60. One thing I know, it's 1 point something. 80 divided by 60. Yeah, it gives us 1.333 kilogram. 1.333 kilogram. Yeah, that is it. That is the mass of the hot water that should be added. I said after studying this, you will never make a mistake of adding a lot of cold water. Then when you are in the shower, it seems you are taking a cold shower. Or you add a lot of hot water. Then when you are in the showers, you start calling your sisters, so your brothers, to bring you water because you are in hell. Otherwise, thank you. It's not in vain. I don't take it in vain that you are watching my channel. You are requested to share, subscribe, and ask for any revision materials you like. Blessings.